In our previous video, we looked at various methods for approximating the area underneath the graph of a function, and that's enclosed between that graph and the x-axis. So we looked at things like left-hand and right-handed Riemann sums, also the midpoint Riemann sum or midpoint rectangle approximation, as well as looking at some other geometric shapes like trapezoids and even triangles. And these were all fine approximations, but we also saw that they varied pretty wildly in terms of giving us a sense of what the area underneath the curve was. For example, look at the circumscribed rectangles here versus the inscribed rectangles. We see that the circumscribed rectangle approximation was almost twice as much as what our inscribed rectangle approximation was. And when we started looking at various ways of approximating this same function over and over again, from right to left-handed Riemann sums to midpoint rectangles to trapezoids, every single one of these is somewhat different. So I said in my previous video that for all of these, it really depended on the function as to which approximation was going to be best. It kind of depended on the shape of the function and what type of geometric shape seemed to match that the best. But is there a way to better our approximation? And at first glance, we might think, oh, maybe perhaps we want to take the average of our left and right-handed Riemann sums, where the left-handed Riemann sum may be an over approximation, and our right-handed Riemann sum in this particular problem was an under approximation. And that would be logical, it would make a lot of sense. But is there a better way to approximate our area underneath the curve? Well, I wanted to kind of pull this graph up here so we could take a look at this. Take, for example, the function sine of x, and let's just say that we're just looking at this function from 0 to pi. And our left-handed bound, or we're going to start our interval from 0, and we're going to go all the way to pi, which is where b is. And suppose we wanted to look at some left-handed Riemann sums here. Well, looking at this here, clearly this is a decent approximation, but it's not great. And it looks like maybe the areas where the rectangle is above the curve might undo the under approximations that we have where the rectangles are underneath the curve. However, it doesn't quite look exact. Can you think of a way that we might be able to better this approximation here? And the answer, hopefully, that what you might stumble upon is that if we increase the number of rectangles that we have here, the more that we increase the number of rectangles, that is to say, we take our entire interval and we divide it by an increased number of n, so that each one of our rectangles now, let me actually even zoom in on this, each one of our rectangles now are getting skinnier and skinnier, right? But in the process, we're able to include more and more rectangles. So we're able to fit more rectangles underneath the curve here. So we're seeing that we're getting a better and better approximation as we increase the number of our partitions. And as we get closer and closer right now, even as I zoom in here, this is a pretty good approximation, but this is even just me going up to n is equal to 100, right? So now the amount of empty space between the number of rectangles that we have and our curve appears to be very minimal. But that's just with 100 rectangles. What if we were to increase the number of rectangles to 1,000, or perhaps even to 1,000,000? Or dare I say, what if we had an infinite number of rectangles here? And if you have been following along with what we've been doing so far in calculus, you could probably see where this is going. If we start to think about the limit of the sum of the area of these rectangles here, we can get not only a good approximation, but actually the exact value of the area underneath this curve. And a way of notating this in calculus is what's known as the definite integral here. So a definite integral is the area, not an approximate area, but the area between the curve and the x-axis. So let me actually jump down to the formal definition of an approximation first so we can get comfortable with our notation. We say the exact value of the area underneath the curve would be what's known as an integral. Let me actually just kind of rewrite this notation here just so we can get a pretty good sense of what we're saying here. So first off, we call this here the lower bound, or the lower limit or bound. And this basically tells us where we're starting. It's the beginning of our interval, And this here would be our upper bound, or our upper limit, if you will. And this is where we stop integrating. This is the quote-unquote end of the interval. Okay, so I'm going to go ahead and do that. Next, we have what's called our integrand. This is our integrand. This is the function that we are integrating. The function we are integrating. And I've already gone through a lot of this notation in our previous video about the indefinite integral, but this is just a quick recap. This is the variable which we are integrating with respect to. And this symbol here that we see, this symbol here that looks kind of like an S, but just kind of stretched out. It's almost like we apply a vertical stretch on the symbol S, or the letter S. And this is to indicate that we are finding the sum. We are finding the sum of all the rectangles here. And you might ask yourself, well, why don't we just use the sigma notation here? Doesn't that represent the sum? And you'd be right, that would give us a sum. However, it's not so much that we are finding the sum of all the rectangles per se, but what we are actually finding, this symbol here actually tells us that we are finding the limit of the sum of our rectangles here. We're finding the limit that this sum approaches as the number of rectangles that we have approaches infinity. It's the limit of the area, or the total sum of all the rectangles area, as the number of rectangles approaches infinity. Now that we're pretty comfortable or familiar now with the notation for the definite integral, I wanted to give you kind of the formal definition here, which gives us something here that looks like this, where we say f evaluated at c sub I times delta x. And at first glance, that looks kind of gnarly, but it really isn't that bad. Let's break each one down. What is f of c sub I? Well, f of c sub I here is simply f evaluated at the beginning of the interval plus I times delta x. So let's go back one step. What is delta x? Let me talk about what delta x is here. Delta x is another way of describing what we call the width of each one of our rectangles. And if you think about it, if our entire interval has a width of b minus a, this is the total width, and then if you divide the total width by the number of rectangles that you have, you're going to have the width of each rectangle, or the width of each subinterval, if you will, or subinterval, which I'll abbreviate there. So that's the width of each one of our rectangles. So if we go back now to looking at what f evaluated at a plus I times delta x, what we're effectively saying is we're going to evaluate the function starting with where the interval starts plus every width of our subinterval. So to make sure that we make sense of this, if we go back to our previous problem back up here, so if we look at this, or actually let's look at this problem here. I think this might be a little bit more helpful. If we're finding the area of this particular rectangle here, so let me just go ahead and highlight that or shade that in. What we're saying is the width is our entire, so we know that our entire width here is 1/2. This entire width of this rectangle is 1/2, which is the width of our entire interval, 2 minus 0, divided by the number of subintervals that we have, which is 4, which is why we get 1/2 for our width. Now, what about for our height? The height of our rectangle is this value here. And what does that represent? It is the output of the function. It's f evaluated at where we started, which in this case is 0, plus 1/2, which is now half a distance over, or half a unit over from where we started. So effectively, it's f evaluated, this is f evaluated at 1/2. Okay, and that's what's going to give us this output here. Well, what about the height of our next rectangle? So again, we have a width of 1/2 here. And now this height here is going to be f evaluated again at 0 plus how many instances of 1/2? 2 times 1/2. So that would be f evaluated at 1, which makes sense. That's what gives us this output here of 3. So we're going to do that over and over again. So we see here every single time what we're just simply noting is where we started, which is A plus I instances of delta x, where our width here is delta x. So that's f evaluated at A plus however many instances of delta x. So if we go back to our definition now, that then tells us that all of this is simply going to give us the height of each rectangle, or the height of each subinterval here. So what we're effectively just doing is we are finding the height times, change colors, the height times the width, which is then going to give us the area of each one of our rectangles. Because if we do height times the width, we're going to get the area of each one of these rectangles. And this sigma notation indicates that we are going to add up the area of each rectangle. How many rectangles are we going to have? We're going to find the limit of this as the number of rectangles that we have then approaches infinity. Again, going back to our, if I were to go back, if I can do this properly, go back to this, we're finding the limit of the sum of all the areas of this interval here, of this region here, if the number of those rectangles approaches infinity. So going back to this, that is what we call the formal definition of our definite integral here. So that gives us now not only just a way of getting a better approximation, but actually the exact value underneath the curve. And in our next lesson, when we talk about the fundamental theorem of calculus, we'll actually discuss how we can find that exact area, using the antiderivative. With that said, there will still be some instances here and there where we're not given the actual function, so there's nothing that we can actually find the antiderivative of, but it would be still a good idea for us to understand how to find the area underneath the curve. So I want to close this lesson with a couple of practice problems, both using our calculator or not, and still making sure we're practicing understanding of how to find the definite integrals using Riemann sums. So take, for example, this particular problem here. Let's find the definite integral of this function from -10 to 10. Now, we don't know what f of x actually is, so there's nothing that we can find the antiderivative for. But we can still find the exact area here by looking at the region underneath and above this curve. Now, this problem highlights a really important idea about definite integrals, and that is to say that when we are finding definite integrals, we now include direction. That is to say, the area, we can be more specific when we're using definite integrals now. We are now finding what's called the signed area. We are finding the signed area underneath the curve. Because if something is below the x-axis, then we would call this a negative area here. So this region here is actually a negative area. Whereas everything above the x-axis, we would call this a positive area. And this makes sense if we, again, think back to the context of what we know about areas underneath curves. That is to say, if we were looking at the velocity of a car, when you have a negative velocity, that means that car is moving backwards, which then means that the distance that the car travels is backwards. So we want to talk about signed area here in all of these cases. So I'm just going to kind of highlight these areas here, or these figures here, and we'll notice that all of these here are geometric shapes that we do know the formulas for, okay? And this final one over here, let's just go ahead and identify that it is indeed a trapezoid, and it's above the x-axis, so we are going to have a positive area. Okay, so let's find the exact area enclosed between the function and the x-axis, taking into account the sign, both positive and negative area. Let's start with this triangle here. So first off, we notice that the area of this triangle, we know the formula is 1/2 base times height. What is the base of our triangle? Well, it doesn't really matter how we orient this, but if we go from -10 to -8, that base is 2. What about that height here? Let me actually make this a little bit smaller so I have some space to work with. What about the height? Now you could write -2 here, but just 2 here is going to be fine as long as we understand that ultimately, once we simplify this, 1/2 of 2 is 1 times 2. Since this is below the x-axis, this area is going to be -2. Okay, now let's find this area over here. We have another triangle. So the area is going to be 1/2. This time our base, we're going from -8 to 0, is a distance of 8. Our height, which is this here, we see is going to be 2. So this area is going to be 8 units squared, and it's going to be +8. Now let's look at this semicircle here. We know this area is pi r squared, all of this divided by 2, because it's a semicircle. And what is the radius in this particular problem? The radius is this distance from 2 to 4. So it's going to be 2 squared, all of that over 2, because again, it's a semicircle. And this is going to come out to 2 pi, but remember that this is a negative area, so we're going to say -2 pi. And then finally, this here is a trapezoid, so we're going to find the average of our heights. And it might be best to think of our height of our trapezoid as this value here. So that's going to be a distance of 2 plus this distance here, which is going to be a distance of 6, all of that over 2, times our quote-unquote base, which is 2. And so this trapezoid has an area of +8. We're now going to add all these up, -2 plus 8 plus 8 minus 2 pi. So let's write that out. So we've got -2 plus 8 plus 8 minus 2 pi. Well, that's just going to give me, you can say this here is equal to 14 minus 2 pi. This is the signed area that is enclosed between this function and the x-axis. Okay? All right. Go ahead now and try some of these practice problems that involve using a calculator to approximate the definite integrals. Now, again, we don't have the functions just yet. We're not concerned yet about trying to integrate these functions, I should say. We'll do that once we've discussed the fundamental theorem of calculus. But let's try to approximate the area here using midpoint Riemann sums. All right. So hopefully you've had a chance to do that. I'll do this first problem here in blue. And the midpoints here are going to occur at 1, 3, and 5. So we're going to evaluate the function at each one of these. And so now we can say this rectangle, its midpoint is at 3. So that's where I'm going to draw the height of the rectangle. And this one is at 5. That's where I'm going to draw the height of this rectangle. And we're going to evaluate the function at each one of these. This is going to be, this coordinate here is 1, 3.32. This here is 3, 4.36. And this value here is 5, 5.92. So we can say that the approximate integral or definite integral of this function is going to be approximately 2 times the sum of all these heights. So if I add all these up, this is going to be approximately 27.183. And if you are using your calculator, which you probably should have been to be finding the heights of these rectangles here, you can actually punch this entire integral into your calculator and see how close your approximation was. All right, and then next up, let's try this problem here. We're going to go this in 2 different ways, actually. We're going to find a right-handed Riemann sum. So we're going to start with a right-handed Riemann sum. So let's do that one first. That's where the right corners of our rectangle are intercepting the function. Oops. So we're going to have something like that. And notice now, there's no way for me to draw a right-handed Riemann sum between 0 and 1. And then this one, we can draw from here to here. Oh, and I probably should have mentioned before, if you read the directions, that we're going 4 equal subdivisions. So in this particular case, I'm able to draw these 4 rectangles here. And then evaluating the function, so here for the right-handed, again, we're doing the right-handed Riemann sum. Each rectangle has a height of 1, or excuse me, a width of 1, not a height. So we're going to say 1. And now we're going to take these heights here of each rectangle. So we had -1.5 This one here is negative 1.5 since we're below the x-axis, plus negative 1. And this one over here has a height of positive 2. So plus positive 2. So this one comes out to approximately negative 1/2. And then let's do a left-handed Riemann sum now. And I'm just going to draw this over the same graph. Hopefully that makes sense. It isn't too confusing. And this is about as far as I can get. I can't draw a left-handed rectangle between 1 and 2 because then you would just really effectively have a rectangle with an area of 0. So if that's the case, now I can shade these in and set these up. This is my left-handed Riemann sum. So I'll identify that. Each of these also have a width of 1. And for this case, I'm going to go negative 1.75 minus 1.5 minus 1. And this area comes out to be negative 4.25 units squared. Okay? All right. So this was a lesson in where we actually learned about the definition of the integral and how it gives us the exact area underneath the curve. And we also went over various methods for approximating the area using various Riemann sums. And if it is a function where we can actually identify that the area underneath the curve is exactly a geometric shape that we know, we can still find the exact area here, provided that we can partition it and find the signed area.